Hello there, and welcome. I'm glad you found your way to this quiet corner of the world. Maybe you've had a long day, your mind filled with the noise of 1,000 small things. Or perhaps you're simply the kind of person who finds a strange comfort in deep, slow thoughts. Whatever the reason, you have arrived, and tonight's journey is for you. You have nothing to do now but rest. There is no list to complete, no problem to solve. Let your mind relax, your breathing slow, and your body grow heavy, as if the very bedrock beneath you is softening to hold your weight. Because tonight, we will drift down into the most patient story there is, the story of stone. We will wander through the quiet, billion-year memoirs of the Earth itself, from the dust of forgotten mountains to the gentle, flowing heart of the planet. This is a world that operates on a time scale of epochs, where the most dramatic events unfold over millions of years. But beneath its silent surface lies a world of gentle motion. Continents adrift on a slow current, crystals growing in perfect darkness. The silent, patient work of water on rock. We will travel gently from the familiar ground underfoot to the unimaginable pressures at the core. Some of what you hear may surprise you, or at least spark a quiet curiosity as you drift away. And just before we begin, if these calm, geological explorations help you unwind, consider liking and subscribing. It simply helps other weary travelers find their way here too. One sleepy soul at a time. Now let's begin. The patient crust. The ground beneath your feet feels permanent, but it is a page in a very slow-moving story. Most of the Earth's crust is made of just 8 elements, quietly assembled. Oxygen and silicon form a gentle partnership, creating the silicate minerals that are the foundation of nearly all the rocks we see. They are joined by aluminum, iron, calcium, and others, all woven together in a crystalline tapestry. This common recipe has been quietly repeating itself for billions of years, the basic quiet language of the solid world. Every single grain of sand was once part of a much larger rock. These tiny fragments begin their journey when larger stones are slowly stressed and weathered. Water freezes in tiny cracks, a gentle, persistent force. Plant roots whisper their way through fractures, seeking nutrients. Over centuries, these quiet actions coax apart the mineral bonds grain by grain. Each speck is a world-worn traveler, carrying the memory of its mountainous origins to a new, softer home. Granite, a rock known for its strength, is actually a mosaic of several different minerals, each cooling at its own pace. As magma deep underground loses its heat over thousands of years, crystals of quartz, feldspar, and mica slowly form and interlock. The quartz hardens first, then the feldspar, with the dark, flaky mica filling the remaining spaces. This patient process creates a speckled, durable stone that often forms the very bones of continents, a testament to slow, deliberate creation. The softest mineral on Earth feels surprisingly smooth to the touch. This is talc, a hydrous magnesium silicate that can be easily scratched with a fingernail. It forms deep within the Earth when heated water and rock interact in a process called metamorphism, transforming harder minerals into this delicate, flaky substance. Its gentle structure is a reminder that not all of the Earth's creations are made of stern, unyielding material. Some are soft whispers from the depths. There are rocks that float. Pumice stone is a volcanic glass, so filled with tiny, trapped gas bubbles that its overall density is less than that of water. It forms when frothy, gas-rich magma is violently ejected from a volcano and cools almost instantly in the air, freezing the bubbles in place. This creates a stone that is paradoxically both born of fire and light enough to drift on the surface of a lake, a porous, quiet vessel. The familiar ring of a struck stone is the sound of its internal structure. Rocks like basalt and some granites have a tight, interlocking crystalline network with very few cracks or pores. When impacted, the sound waves travel efficiently through this rigid lattice, creating a clear, high-pitched ping. Softer, more porous rocks like sandstone absorb the energy, resulting in a dull thud. Each rock, then, has its own quiet voice, a signature of its hidden architecture. The oldest rocks on Earth are quiet, gnarled formations found in the Canadian Shield. These are the Acasta gneiss metamorphic rocks that have been dated to be about 4 billion years old. They have been folded, heated, and compressed so many times that their original form is a mystery, a palimpsest of the planet's most ancient memories. To hold one is to touch a time before continents, before oceans, before life itself, a patient, silent witness. We don't know exactly how the first continents formed, but they likely began as thin, buoyant scum on the surface of a global magma ocean. As the young Earth cooled, minerals like feldspar, which are less dense, would have crystallized and floated to the top, slowly accumulating into the first tiny proto-continents. This was not a sudden event, but a slow, patient gathering over hundreds of millions of years, the first gentle stitching of the world's fabric. The soil you walk on is not just dirt. It is a memory bank of the landscape. It holds fragments of the local bedrock, grains of sand carried by ancient winds or rivers, and the decomposed remains of countless generations of plants and animals. A single handful is an archive, telling a story of geological patience and biological cycles working in a slow, intertwined partnership. It is the Earth's gentle, living skin. The concept of deep time was first grasped by looking at layers of rock. In the 18th century, James Hutton observed the slow processes of erosion and sedimentation and realized that for mountains to be worn down and new rocks to form from their dust, the Earth must be unimaginably old. He saw no vestige of a beginning, no prospect of an end. This was the quiet, humbling realization that the crust operates on a timescale that gently dwarfs all human concern. The sculpting forces. The most powerful force in shaping our landscapes is not the earthquake or the volcano, but the patient, persistent fall of water. A single raindrop falling on a mountainside carries a tiny pulse of energy. It splashes against the soil, dislodging a few minute grains. Over millions of years and trillions upon trillions of raindrops, this gentle percussion carries entire mountain ranges, grain by grain, down to the sea. It is a symphony of soft impacts, composing vast canyons and wide, fertile plains. The Grand Canyon was not carved by a single, violent event, but by a gentle, persistent ribbon of water. The Colorado River has been flowing for 5 or 6 million years, slowly deepening its channel as the Colorado Plateau gradually rose around it. The river acted like a slow-moving saw, patiently cutting down through layer after layer of rock, exposing nearly 2 billion years of Earth's history without ever hurrying. It is a monument to the power of a steady, focused flow. Water does not only carve from the outside, it also sculpts from within. As rainwater percolates through the soil, it absorbs carbon dioxide, becoming a weak acid. This slightly acidic water then seeps into fractures in limestone, slowly dissolving the rock away over thousands of years. This hidden chemical artistry creates vast, silent caverns and intricate cave systems, all formed in perfect darkness by the gentle, dissolving kiss of water. The smooth, rounded shapes of river stones are a testament to a long and gentle journey. A sharp, angular rock, tumbled along a riverbed for miles and years, is slowly smoothed as it collides softly with other stones. These are not violent impacts, but a gradual, rhythmic knocking that wears away all the hard edges. Each rounded stone is a well-traveled pilgrim, its shape telling a silent story of a long, watery path from the highlands to the sea. Even the hardest granite mountain is slowly softened by the gentle force of frost. When water seeps into a tiny crack and freezes, it expands by nearly 10%. This expansion exerts a gentle but immense pressure, patiently prying the rock apart. Over countless freeze-thaw cycles, a hairline fracture can be slowly widened into a gaping crevice. It is a quiet, relentless force, using the simple transformation of water to ice to slowly dismantle the mightiest of stone fortresses. Some of the most dramatic rock formations are shaped not by liquid water, but by the patient scouring of wind. In vast deserts where there is little vegetation to hold the soil, wind picks up fine particles of sand and silt. Acting like a gentle, invisible sandblaster, the wind slowly polishes rock surfaces, carving them into intricate shapes like arches and hoodoos. These landforms are not built up, but are what remains after the wind has slowly carried everything else away. The very air we breathe is a gentle sculptor. Oxygen in the atmosphere slowly reacts with iron-rich minerals in rock, in a process we call rust. This oxidation causes the minerals to change, to weaken, and to slowly crumble apart. A rock that appears solid may be quietly turning to powder from within, its internal structure gently transforming through its long, slow conversation with the air. It is a reminder that even the invisible can, in time, reshape the solid. We don't always know why a river begins to meander, but once the gentle curve begins, it perpetuates itself. Water flowing on the outside of a bend moves faster, eroding the bank, while on the inside, where the water is slower, sediment is deposited. This slow, feedback-driven dance causes the river to loop and curl across its floodplain in beautiful, sinuous patterns. It is a self-made labyrinth, drawn patiently onto the landscape by the water's own, unhurried flow. Glaciers are rivers of ice that flow with a patience that is almost beyond comprehension. Under the immense weight of accumulated snow, the ice below becomes plastic and begins to drift downhill, sometimes only a few centimeters a day. As it moves, it grinds the bedrock beneath it, polishing it smooth or plucking entire boulders from the earth. The vast U-shaped valleys and serene, scooped-out lake basins of the world are the gentle, slow-motion fingerprints of these ancient, icy travelers. The gentle force of life itself is a powerful geological artist. A tiny lichen, a partnership of fungus and algae, can colonize a bare rock surface. It secretes weak acids that slowly dissolve the mineral grains, and its tiny root-like structures pry into microscopic cracks. Over centuries, a community of lichens can prepare a rock surface for larger plants, beginning the slow, beautiful process of turning bare stone into fertile soil. Life, in its quietest forms, is a patient stonecutter. The deep-time tapestry, the pages of Earth's history, are not made of paper but of stone. Sedimentary rock layers, known as strata, lie upon one another like a silent library. The oldest stories are at the bottom, with younger chapters gently laid on top over the eons. This simple, profound order is the principle of superposition, the gentle logic that allows us to read the planet's autobiography, written in mud, sand, and ash, that slowly turned to stone. A fossil is not always the bone itself, but often a stone memory of the bone. When an organism is buried in sediment, mineral-rich water can slowly percolate through the remains. Over millions of years, the original material dissolves away, molecule by molecule, and is replaced by minerals like silica or calcite. This process, called permineralization, creates a perfect stone copy, a quiet echo of a life that once was, preserved in crystalline detail. The most common fossils are not of giant creatures, but of small, quiet lives. Countless shells, crinoid stems, and trilobite fragments are entombed in limestone and shale. These organisms lived in vast numbers in ancient seas, and when they died, their hard parts settled gently to the seafloor to be buried by silt. They form whole rock layers, a whispering bed of limestone made entirely from the accumulated memories of ancient marine life. There are moments in the rock record where entire worlds seem to vanish. These are unconformities, vast gaps in time, where layers of rock are missing, representing millions or even hundreds of millions of years that erosion quietly erased. It is a lost chapter in the Earth's story, a quiet hiatus where the tape simply stopped recording. We don't know all the stories that were lost in these silent intervals, only that time, as always, flowed onward. Some fossils capture not the hard parts of an organism, but a single, fleeting moment of its existence. A dinosaur's footsteps pressed into soft mud that later hardened into stone tell a story of a journey taken one ordinary afternoon. The ripple marks of an ancient shoreline, frozen in sandstone, speak of gentle waves under a forgotten sun. These trace fossils are the most delicate threads in the tapestry, preserving not the body, but the breath and motion of deep time. The color of rock tells a quiet story about its ancient environment. Red and brown sandstones often get their hue from iron oxide rust, which forms in the presence of oxygen, suggesting these rocks were laid down on land or in shallow, sun-warmed waters. Dark grey or black shales, rich in organic carbon, whisper of deep, stagnant basins where decay was slow and oxygen was scarce. The Earth's palette is a gentle record of ancient air and water. We don't know the identity of most of the life that has ever existed, for the fossil record is inherently gentle and incomplete. For a creature to be fossilized, a series of perfectly quiet chance events must occur: rapid burial, the right chemical conditions, and the luck to avoid being crushed or dissolved over the eons. The vast majority of life has simply returned its energy to the system, leaving no stone memory behind. The tapestry is beautiful, but full of quiet, empty spaces. The first evidence of life on Earth is not a bone or a shell, but a subtle chemical signature. In rocks over 3.5 billion years old, scientists have found a particular ratio of carbon isotopes that is often a gentle fingerprint of biological activity. It suggests that single-celled organisms were already living, breathing, and altering their environment in the planet's infancy, leaving a faint, molecular whisper in the oldest stones. Coal is a fossil too, a dense, black tapestry woven from ancient sunlight. It forms from vast accumulations of plant matter, giant ferns and trees from swampy carbon period forests that were buried and gently compressed over millions of years. The heat and pressure slowly drove off the gases, leaving behind a carbon-rich residue. When we burn coal, we are releasing sunlight captured by plants hundreds of millions of years ago, a slow, stored fire from a lost world. The entire geological timescale is a human construct, a gentle attempt to impose order on deep time. Eons, eras, and periods are like chapters we have drawn in the rock, their boundaries often marked by a significant change in the fossils found there. The line between the Cretaceous and the Paleogene, for instance, is a thin, dark layer of clay rich in iridium, a silent, global marker of a profound transition. We have given names to the silence, finding rhythm in the patient accumulation of stone, the unseen depths. We live on the thinnest of skins, a crust that is to the earth what the film on a pond is to the water beneath. Beneath the familiar rocks we can touch lies the mantle, a vast rocky layer nearly 3,000 kilometers thick. It makes up most of our planet's volume, a world of solid stone that nonetheless flows with an unimaginable patience. We have never seen it directly, only inferred its presence from the gentle whispers it sends to the surface. The deepest hole ever drilled by humans penetrates only the outermost pages of Earth's story. The Kola super-deep borehole in Russia reaches just over 12 kilometers down, a staggering achievement that yet barely scratches the crust. The heat and pressure at that depth became so immense that the rock itself began to behave like a plastic, gently closing the hole. It serves as a humble reminder of the profound, inaccessible depths that lie forever beyond our direct reach. We know the structure of Earth's deep interior not by digging, but by listening. When a large earthquake occurs, it sends seismic waves pulsing through the planet. By tracking how these waves speed up, slow down, or bend as they journey through the Earth, scientists can gently map its internal structure. It is a form of celestial echolocation, using the planet's own deep tremors to illuminate the boundaries of the crust, the mantle, and the core. The boundary between the crust and the mantle is a profound transition known as the Mohorovičić discontinuity, or simply the MOHO. Here, the familiar rocks of the crust give way to the denser, ultramafic rocks of the upper mantle. The seismic waves change their speed abruptly at this interface, telling us of a chemical and physical change that circles the entire globe. It is the true universal floor of the ocean basins and the foundation of the continents, a silent, unseeable frontier. The rock of the Earth's mantle is solid, but over millions of years it can flow. Under the immense heat and pressure of the deep Earth, the atomic structure of mantle minerals can slowly deform, allowing the rock to creep and circulate in vast, convective currents. This is the slow, hidden engine of plate tectonics, a circulation system that turns over the entire mantle once every billion years or so, with a rhythm that is the heartbeat of the planet. We don't know the exact composition of the lower mantle, for its conditions are impossible to fully recreate. At depths beyond 600 kilometers, the pressure is over 1 million times that of the surface atmosphere. Scientists believe that common minerals like olivine transform into denser, more compact crystalline structures, like those of the mineral bridgmanite. But this remains a theory, a best guess, at the nature of the planet's largest, most mysterious layer. There may be entire mountains hidden at the core mantle boundary, a landscape we will never see. Seismic data suggests there are vast, mysterious regions where the rock is unusually dense or exceptionally hot. Some scientists propose there are anticontinents of sunken oceanic crust and towering peaks that dwarf any mountain on the surface. This hidden topography, thousands of kilometers below, gently influences the flow of heat from the core and the convection of the mantle above. The extreme conditions of the mantle can create rare and beautiful diamonds. These gems form from carbon atoms subjected to the immense pressure of about 150 kilometers down and temperatures over 1,000 degrees Celsius. They are then carried to the surface in violent but geologically brief volcanic eruptions. A diamond is thus a messenger from the deep mantle, a crystal that holds within its perfect lattice a memory of the abyssal pressure and heat. The source of the heat that drives the Earth's inner engine is a mixture of ancient and ongoing processes. Some is left over from the planet's violent formation, the residual energy of countless collisions. The rest comes from the slow, quiet decay of radioactive isotopes of elements like potassium, uranium, and thorium, scattered throughout the mantle and core. The Earth's heart is warmed by both the memory of its birth and a gentle, radioactive glow that has persisted for billions of years. The very center of the Earth is a world of its own, a core composed primarily of iron and nickel. The outer core is a swirling liquid metal ocean, and its motion generates the planet's protective magnetic field. Within that, the inner core is a solid ball, a crystal of iron under such fantastic pressure that it remains solid despite a temperature rivaling the surface of the Sun. We understand it only as a mathematical certainty, a silent incandescent heart at the center of our world, forever beyond our sight. The birth of mountains. The highest mountains on Earth are also some of the youngest. The Himalayas, with their soaring peaks, began their gentle rise only about 50 million years ago. when the Indian subcontinent slowly met the southern edge of Asia. This was not a sudden, violent crash, but a patient, relentless convergence that continues to this day, pushing the land skyward at roughly the same speed your fingernails grow. The summit of Everest is thus not a static point, but a slowly climbing pilgrim. Most of the world's great mountain ranges are born from the slow-motion collision of tectonic plates. When two continental plates meet, neither is dense enough to be subducted back into the mantle. Instead, their edges crumple, fold, and thicken over millions of years, like the gentle wrinkling of a rug pushed against a wall. The Alps, the Appalachians, and the Urals were all formed this way, their roots extending deep into the crust, a testament to the patient pressure of drifting continents. Not all mountains are built by collision. Some are born from tension. As the Earth's crust is gently pulled apart, as it is in East Africa's Great Rift Valley, large blocks of land can slowly sink between parallel faults, while the intervening blocks remain standing. These are fault block mountains with long, gentle slopes on one side and steep, rugged escarpments on the other. They are not pushed up, but are the quiet, resilient pieces left behind as the world slowly stretches and thins. Before a mountain range rises high, its roots sink even deeper. According to the principle of isostasy, the thick crust beneath a mountain range extends down into the denser plastic mantle, much like an iceberg floats in water. The towering peaks we see are just the visible tip of a vast, deep foundation of crustal rock. The mountain, therefore, is both what rises to the sky and what sinks into the earth, a perfect, balanced architecture of light and heavy stone. The dramatic, folded layers of rock seen in mountain cliffs are a record of immense but patient force. When sedimentary rocks are caught in a tectonic collision, they are too brittle to be pushed as a single block. Instead, they slowly bend and deform, creating vast, graceful folds called anticlines and synclines. These waves of stone, frozen in mid-curl, tell a story of a landscape that was once as soft and pliable as clay, slowly shaped by pressures that worked over millions of years. Volcanic mountains are built not from the crumpling of rock, but from the gentle accumulation of its own tears. As a tectonic plate moves over a stationary hotspot in the mantle, magma periodically finds a pathway to the surface. Each eruption, whether explosive or a quiet lava flow, adds a new layer to the growing peak. The Hawaiian Islands are a perfect chain of such mountains, each volcano a quiet monument built from countless individual outpourings of the Earth's interior. We don't always know why some mountains stand alone as solitary sentinels. A monadnock like Mount Katahdin in Maine or Uluru in Australia is a solitary peak that rises abruptly from a surrounding plain of erosion. These are often the last, most resilient remnants of a vast, ancient plateau that has been almost completely worn away by wind and water over eons. They are not young mountains, but the weathered elders of a lost highland world standing in quiet, enduring defiance. The process of mountain building, or orogeny, is a cycle that has repeated itself throughout Earth's long history. Ancient mountain belts like the worn-down Appalachians whisper of colossal peaks that once rivaled the modern Himalayas hundreds of millions of years ago. They have been gently smoothed by time, their roots all that remain at the surface. This cycle of uplift and erosion, of birth and quiet decay, is one of the planet's most enduring and patient rhythms. Some of the most dramatic mountainscapes are carved not by uplift but by ice. During the Ice Ages, vast glaciers flowed through existing river valleys, scouring and deepening them into U-shaped troughs. When the ice eventually retreated, it left behind sharp, jagged ridges called arêtes and towering, pyramid-shaped peaks known as horns. The Matterhorn is such a peak, a masterpiece of glacial sculpture, its form chiseled by the slow, patient flow of ice. The birth of a mountain is never truly over. Even as tectonic forces slowly push a range upward, the opposing forces of erosion, rain, wind, and ice, immediately begin to wear it down. A mountain's ultimate height is not a fixed number, but a gentle, dynamic balance between these two immense, slow-moving powers. It is a quiet, persistent dialogue between the Earth's inner heat, which builds, and its atmosphere, which patiently dismantles. A mountain is not an object, but a slow event. The rock cycle's rhythm. Every rock on Earth is a temporary state in a slow, endless dance. The rock cycle has no true beginning or end, only a gentle, continuous flow of material from one form to another. A grain of sand on a beach may once have been part of a mountain's granite heart, and may one day be compressed into sandstone or drawn deep into the earth to be reborn as a new, crystalline structure. It is the planet's most patient and fundamental recycling program. Igneous rocks are the primal matter, the starting point of the cycle. They form from the cooling and solidification of molten magma, whether deep underground over millennia or on the surface in a rapid, volcanic sigh. Granite crystallizes slowly in the darkness, allowing large minerals to grow, while basalt chills quickly in the air or water, creating a fine-grained, dark stone. All other rocks begin their story from this fiery origin, the Earth's first solid breath. Sedimentary rocks are the quiet archivists of the surface world. They form from the weathered fragments of other rocks, the mineral shells of organisms, or minerals precipitated from water, all gently layered and compressed over time. Sand becomes sandstone, mud becomes shale, and calcium carbonate from sea creatures becomes limestone. These rocks are a tapestry, woven from the broken pieces of the past, telling stories of ancient rivers, seas, and deserts. Metamorphic rocks are the quiet transformers, changed by heat and pressure, but never melting. Deep within the Earth's crust, existing rocks are gently cooked and squeezed, causing their minerals to recrystallize into new forms. Shale becomes slate, limestone becomes marble, and granite becomes gneiss with its characteristic swirling band. This is a process of renewal in the solid state, a patient alchemy that creates beauty from what was already there. The spark that drives the entire rock cycle is the Earth's internal heat. This gentle, radioactive warmth from the planet's core provides the energy to melt rocks into magma, which then rises to form new, igneous rock. It also drives the tectonic plates, whose collisions build mountains and bury rocks, subjecting them to the heat and pressure that cause metamorphism. This deep, slow fire is the quiet engine of geological change. Water is the gentle courier of the rock cycle. It dissolves minerals from rocks during chemical weathering and carries the tiny fragments of physical weathering downstream. These dissolved ions and sediment grains are the raw materials for sedimentary rocks. Water also percolates down into the crust, where it can lower the melting point of rock, facilitating the creation of new magma. And it is essential for the formation of many ore deposits. Its flow connects every part of the cycle. There are rocks that seem to straddle the boundaries of the cycle, embodying a state of gentle transition. A migmatite is a beautiful mixed rock that forms when the temperature is so high that some parts begin to melt, forming igneous-looking veins, while other parts remain solid and metamorphic. It is a rock caught in the act of becoming, a frozen moment in the slow journey from one state to another. A testament to the fluidity of stone. We don't know the exact journey of any single mineral grain, only the possible paths laid out by the cycle. A crystal of quartz could spend 200 million years as part of a granite mountain, then another 50 million as a grain of sand in a desert, before being subducted and transformed into a new mineral in a metamorphic rock. Its biography is written in deep time, a story of endless travel and transformation that is mostly lost to us. The rock cycle is a planetary scale system of renewal, ensuring that no part of the crust is permanent. Old continents are slowly worn down, their sediment carried to ocean basins, which may eventually be subducted, melted, and their material used to build new continental crust at volcanic arcs. This gentle, continuous overturn has been happening for over 4 billion years, constantly reshaping the face of the planet and redistributing its chemical elements. The rhythm of the rock cycle operates on timescales that gently dwarf human perception. A single complete turn for a volume of rock, from igneous to sedimentary to metamorphic, and back to igneous, may take hundreds of millions of years. It is a slow, stately rhythm, a pulse that beats in time with the convection of the mantle and the drift of continents. To understand it is to appreciate the profound, patient recycling that is the true nature of our solid world. The crystal kingdom. The beauty of a crystal begins in a realm far below what the eye can see. Every crystal is an orderly arrangement of atoms, a repeating three-dimensional pattern we call a lattice. This hidden architecture dictates the crystal's eventual shape, the way it breaks, and how it interacts with light. A perfect diamond and a grain of table salt share this same underlying principle, a silent, geometric order born from the patient habits of atoms linking together. The six-sided symmetry of a snowflake is a gentle echo of the water molecule's own hidden architecture. As water vapor freezes in the clouds, the hydrogen and oxygen atoms arrange themselves in a hexagonal lattice, a pattern that prefers 60-degree angles. The branching, intricate arms of the snowflake form as the crystal grows, its unique shape a quiet record of its journey through the atmosphere, a frozen diary of temperature and humidity. Most gemstones are not rare in their chemical composition, but in the perfect conditions required for their formation. An amethyst is, at its heart, simply quartz, one of the most common minerals on Earth. Its majestic purple color comes from traces of iron embedded in its crystal lattice and exposure to natural radiation over millions of years. The perfect six-sided prisms form only when there is space to grow slowly in the quiet, chemical-rich waters within a geode. The different shapes of crystals, from cubes to pyramids to delicate needles, are known as their habits. A crystal's habit is a gentle expression of its internal atomic structure and the environment in which it grew. Halite, or rock salt, almost always forms perfect cubes because its sodium and chlorine atoms arrange themselves in a cubic lattice. When conditions are ideal and space is ample, a crystal will grow to exhibit its perfect geometric habit, a quiet unveiling of its inner self. Some minerals have the gentle ability to grow in forms that mimic other, more complex shapes. Pyrite, or fool's gold, often forms perfect cubes, but it can also crystallize into 12-sided shapes called pyritohedrons, or even into delicate, radiating needles that look like organic forms. These variations are not mistakes, but alternative expressions of the same iron and sulfur atoms, arranging themselves in response to subtle changes in their chemical environment. The vibrant green of an emerald is a gift from a tiny, hidden guest within its crystal structure. Emerald is a variety of the mineral beryl which is colorless in its pure form. Its iconic color comes from trace amounts of chromium or vanadium atoms that quietly substitute for aluminum in the crystal lattice. These foreign atoms absorb certain wavelengths of light, allowing only the soft green light to pass through and reach our eyes, a hidden key that unlocks a world of color. We don't always know why some crystals grow to immense sizes while others remain microscopic. In the Cave of the Crystals in Mexico, selenite gypsum crystals have grown to the size of telephone poles over hundreds of thousands of years. This was only possible because the cave was filled with mineral-rich water maintained at a perfectly stable high temperature by the magma below. It was a unique, patient nursery that allowed these giants of the Crystal Kingdom to slowly emerge. The smooth, flat surfaces of a crystal are called faces, and the angles between them are constant for every mineral. This is the law of constancy of interfacial angles, a gentle rule of the Crystal Kingdom. No matter how distorted or large a quartz crystal may grow, the angle between its prism faces will always be exactly 120 degrees. This constancy is a direct reflection of the unchanging internal lattice, a hidden geometry that expresses itself with perfect fidelity. Opals hold their shimmering play of color not from a rigid crystal lattice, but from a gentle architecture of spheres. Precious opal is made of tiny hydrated silica spheres, all of a similar size, packed together in a regular pattern. The spaces between these spheres act as a diffraction grating, bending white light and separating it into the full spectrum of colors. An opal's fire is thus a soft, structural color, a rainbow born from the orderly stacking of microscopic beads. The transformation of graphite into a diamond is a story of profound patience and pressure. Both are made purely of carbon, but their atoms are arranged in utterly different lattices. Graphite has atoms in flat, sliding sheets, while in a diamond, each carbon atom is strongly bonded to 4 others in a rigid, three-dimensional network. This transformation requires the gentle, immense pressure of the Earth's mantle, about 150 kilometers down, which slowly rearranges the atomic bonds to create the hardest natural substance. The ground beneath your feet. The soil is not merely dirt, it is a living, breathing skin upon the earth. A single teaspoon of healthy soil contains more microorganisms than there are people on the planet. It is a universe of bacteria, fungi, protozoa, and tiny insects, all working in a quiet symbiotic dance to break down organic matter and recycle nutrients. This vibrant, hidden ecosystem is the gentle foundation for all life on land, a soft, bustling city beneath our feet. The color of soil is a quiet language telling the story of its history. Rich, dark brown or black soils are often high in organic matter, the decomposed remains of plants and animals, creating a fertile ground. Red and yellow soils whisper of iron oxides, rusting slowly in a well-drained, aerated environment. The pale, greyish soils of wetlands suggest a lack of oxygen, where decomposition is a much slower, more gentle process. The Earth paints its own biography in subtle hues. Sand is the universal traveler, a collection of world-worn fragments. Every grain has a story of a long journey, having been weathered from a larger rock, tumbled down rivers, or drifted on ancient winds. The smooth, rounded grains of a beach have been polished by the endless, gentle massage of waves. The fine, red sands of deserts carry the iron oxide signature of the ancient rocks from which they came. To walk on sand is to walk on a library of eroded landscapes. The gentle, earthy scent that rises after a rain has a name, petrichor. This fragrance comes from a combination of oils released by plants during dry periods and a compound called geosmin, produced by soil-dwelling bacteria called actinomycetes. When rain hits the dry ground, it disturbs these molecules and carries them into the air as a fine aerosol. That comforting smell is the breath of the soil itself, a quiet perfume released by the earth to greet the water. Loess is a special, silty soil that has traveled on the wind. These vast, fertile deposits found in places like the American Midwest and parts of China were laid down by ancient glaciers. As the glaciers retreated, they left behind fine rock flour, which was then picked up by the wind and carried for hundreds of miles, settling in thick, blanket-like layers. The prairies and breadbaskets of the world are often built upon this gentle, wind-blown gift from a colder age. We don't always know the precise origin of every patch of soil. for it is a complex, ever-changing mixture. It is part mineral from the weathered local bedrock, part organic from the cycle of life and death, part water and part air. It is a recipe that has been slowly stirred by worms, insects, and roots for centuries. Your local soil is a unique, living tapestry woven from the geology, biology, and climate of your specific corner of the world. The humble earthworm is a gentle engineer of the ground. As it burrows, it aerates the soil, allowing oxygen to reach deeper and water to infiltrate more easily. It consumes organic matter, breaking it down and enriching the soil with its castings. Charles Darwin calculated that earthworms could slowly, over time, bring up to 10 tons of fine soil to the surface per acre each year. They are constant, quiet caretakers, tirelessly tilling and enriching the Earth's skin. A footprint in soft mud is a fleeting fossil, a gentle impression of a moment in time. Under the right conditions, such impressions can be buried by new sediment and harden, preserving that momentary pressure for millions of years. Paleontologists find the footprints of dinosaurs, early humans, and ancient mammals, each one a silent record of a single step. Your own footprints, though they may wash away with the next rain, are part of this same gentle tradition of leaving a mark. The concept of terra firma, solid ground, is a deeply comforting human idea. In a world of uncertainty, the ground is what holds us, supports our homes, and grows our food. This personal connection is woven into our language. We speak of being down to earth or having our feet on the ground. The soil is the physical foundation of our lives, the steady, patient platform upon which we build our existence, a constant and gentle presence. The ground you walk on contains atoms that have been part of countless previous worlds. The calcium in your bones was once part of a limestone seabed. The iron in your blood was forged in the heart of a long-dead star and found its way into the Earth's crust. The very air you breathe has been cycled through volcanoes and plants for eons. You are not just on the Earth, you are of it. Your physical connection to the ground beneath your feet is a literal, atomic bond to the planet's deep and living history. From continent to atom, the map of the world is not a permanent image, but a single frame in a very slow-moving film. The continents we know are fragments of the ancient supercontinent Pangaea, which itself was just the latest assembly in a cycle that has repeated every few 100 million years. Before Pangaea, there was Rodinia, and before that, other forgotten giants. The continents are slow, stately travelers, drifting apart and coming together over spans of time that gently dwarf the entire history of complex life. The force that moves continents is a gentle, persistent heat from the Earth's deep interior. The planet's mantle, though solid, flows with a plasticity that allows it to convect, rising slowly in some places and sinking in others, over cycles of 100 million years. This slow, churning motion in the Earth's mantle is the invisible engine that drags the tectonic plates along, a deep, thermal pulse that rearranges the face of the world 1 centimeter per year. From the scale of a continent, we can drift down to a single mountain range like the Himalayas. This vast crumple zone, stretching over 2,000 kilometers, is the result of 2 continental plates meeting. Yet this colossal feature is, from a planetary perspective, a mere wrinkle on the Earth's crust. The entire range, for all its grandeur, represents only the lightest thickening of the planet's outermost skin, a gentle buckling in the slow collision of 2 immense, drifting land masses. We don't know the exact configuration of the next supercontinent, but we know the cycle will continue. Scientists project that in about 250 million years, the continents may coalesce again into a new landmass, sometimes called Pangaea Proxima. The Atlantic Ocean may slowly close while the Pacific widens, bringing the Americas back into a gentle collision with Eurasia and Africa. It is a future world whose outlines we can only softly predict, a ghost of geography yet to be born. From a mountain range, we can focus on a single boulder, a piece of granite. This rock, which seems so monolithic, is itself a community of minerals. Interlocking crystals of milky quartz, pink feldspar, and black mica are all visible to the naked eye. Each of these minerals has a different composition and a different story of crystallization from the cooling magma. A diverse neighborhood of crystals locked together in a solid, stony embrace. Within that granite, a single crystal of quartz tells a deeper story. Its hexagonal prism shape is a direct expression of its internal, atomic architecture. This visible form is the macroscopic result of a precise, repeating pattern of silicon and oxygen atoms. The crystal you can hold in your hand is the final, polished product of a hidden, geometric order that extends down to a scale far beyond our sight, a bridge between the hand and the atom. That quartz crystal is built from a fundamental unit called a silica tetrahedron. One silicon atom bonded to 4 oxygen atoms in a pyramid-like shape. This tiny, robust building block is the reason for quartz's hardness and stability. In the crystal lattice, these tetrahedra share their oxygen atoms with their neighbors, linking together in a continuous 3-dimensional framework that is both strong and beautifully symmetrical. The secret heart of the crystal. The scale of geology stretches from the drift of continents over thousands of kilometers to the vibration of atoms over distances smaller than a nanometer. A single millimeter of limestone may represent 1,000 years of gentle sedimentation on an ancient seafloor. A continent may move 10,000 kilometers in the time it takes for a radioactive atom in a mineral grain to decay. Geology is the science that gently weaves together the cosmic and the atomic, the immensely vast and the infinitesimally small. You are a being that exists at the midpoint of these scales. You are large enough to feel a grain of sand between your fingers, yet too large to perceive the molecular structure that gives it form. You can see a mountain on the horizon, but your life is too brief to witness its slow rise and fall. Your existence is a gentle, momentary balance, a point of awareness floating between the slow dance of continents and the silent, frantic dance of atoms. Every geological process, no matter how grand, is ultimately a story of atomic interactions. The rusting of a rock is the slow oxidation of iron atoms. The growth of a crystal is the patient addition of atoms to a lattice. The very convection of the mantle is driven by the gentle heat released from the decay of radioactive atoms like potassium-40 and uranium-238. From the largest continent to the smallest grain, it is all a quiet, continuous narrative written in the language of chemistry and physics. The pulse of water and stone. The water you drink today has been part of the Earth's slow, rhythmic dance for billions of years. It has evaporated from ancient seas, fallen as rain on dinosaurs, been frozen in glaciers, and seeped through deep aquifers. The total amount of water on Earth is essentially constant, endlessly cycling through the atmosphere, the land, and the oceans. This is the grand hydrological cycle, the planet's gentle, perpetual circulation of its most vital substance. The journey of a raindrop, once it meets the land, is a quiet choice between 2 paths. It may join the surface runoff, beginning its gentle flow downhill, gathering with other drops to form a stream, then a river on its way back to the sea. Or it may choose a slower, more hidden path, percolating down through the soil and into the spaces within rocks, becoming part of the vast, slow-moving world of groundwater. This is the first soft branching in water's long journey home. Groundwater does not flow in raging underground rivers, but moves with a profound patience through porous and permeable rock. It seeps through the tiny, connected spaces between sand grains or through the fractures in harder stone like limestone or granite. Its pace is often measured in meters per year, a slow, persistent ooze that can take centuries or millennia to travel just a few miles. It is the Earth's hidden reservoir, a secret, sluggish ocean within the stone. The upper surface of the groundwater is called the water table, a gentle, unseen landscape that mirrors the topography of the land above. It rises slowly beneath hills and dips under valleys. In a wetland, the water table is at the surface. In a deep desert, it may lie hundreds of feet down. This hidden surface breathes with the seasons, rising after rains and slowly falling during droughts, a quiet, rhythmic pulse in the dark. Caves are the gentle architecture carved by groundwater's slow, chemical patience. As rainwater, slightly acidic from carbon dioxide in the air and soil, seeps into limestone, it dissolves the calcium carbonate molecule by molecule. Over hundreds of thousands of years, this slow dissolution enlarges fractures into vast, interconnected caverns. A cave is not built but subtracted, a hollowed-out space where solid rock once was, a testament to water's quiet, dissolving work. We don't always know the full extent of a cave system, for its passages can wind for miles in perfect darkness. Some of the world's largest caves, like Mammoth Cave in Kentucky, are still being gently explored and mapped. Their formation is an ongoing process, as acidic water continues to work its way down from the surface, slowly dissolving new passages and creating a complex, three-dimensional labyrinth that may never be fully known. The beautiful formations within caves, known as speleothems, are created when the cave-making process gently reverses. Water saturated with dissolved calcite drips from a cave ceiling. When a drop hangs and loses its carbon dioxide, it cannot hold the mineral anymore, and a tiny ring of calcite is deposited. Over millennia, these rings build into a stalactite hanging like a stone icicle. Where the drops land, a stalagmite grows upward from the floor, a patient, reciprocal dance of deposition. The hot water that feeds geothermal springs has often traveled a very long and deep path. Surface water can percolate down several kilometers into the Earth's crust, where it is warmed by the natural geothermal gradient or by proximity to magma. This heated water becomes less dense and begins a slow, buoyant journey back to the surface, rising along fractures to emerge as a hot spring or a geyser, having been warmed by the Earth's inner heart. An artesian well is a gentle testament to the pressure that can build in confined groundwater. This occurs when water is trapped between two impermeable layers and the recharge area is at a higher elevation than the well. The weight of the water in the recharge area creates pressure, so when the confining layer is punctured, the water rises naturally, sometimes all the way to the surface, without need for a pump. It is a simple, elegant display of hydraulic potential, a quiet fountain born from gravity and geology. The entire cycle of water and stone is a slow, rhythmic conversation. Water wears down mountains and carries their sediment to the sea, where it may be compressed into new stone. That new stone may be uplifted by tectonic forces to form new mountains, which will, in turn, be slowly dissected by water once again. This great, gentle loop of erosion and uplift, of dissolution and deposition, is one of the oldest and most patient dialogues on our planet, a pulse that has beat for billions of years. The Earth's quiet energy, the warmth you feel underfoot on a sunny day, is only the faintest echo of the immense heat residing within the Earth. For every square meter of the planet's surface, about as much heat gently radiates out from the interior as from a single small candle. This geothermal flow is the quiet, steady breath of the planet, a remnant of its fiery formation and the slow, persistent decay of radioactive elements deep within the rock. The source of the Earth's internal heat is a blend of ancient memory and ongoing process. Some is primordial, left over from the colossal collisions and gravitational compression that formed the planet over 4.5 billion years ago. The rest is generated gently and continuously by the decay of long-lived radioactive isotopes like potassium-40 and uranium-238, scattered throughout the mantle and core. The planet's heart is kept warm by both the echo of its birth and a soft, radioactive glow. We don't know the exact temperature at the very center of the Earth, but we can gently estimate. Based on the behavior of seismic waves and experiments with minerals under extreme pressure, scientists believe the inner core is a solid ball of iron and nickel with a temperature around 5,700 degrees Celsius, similar to the surface of the Sun. Yet this fantastic heat is contained under such immense pressure that the metal remains solid, a silent, incandescent heart. The Earth's magnetic field is an invisible, protective embrace generated by the churning of the liquid outer core. This swirling ocean of molten iron and nickel acts as a vast, slow dynamo, converting the planet's rotational energy and thermal heat into a magnetic field that stretches far out into space. It is a gentle, perpetual motion, a cosmic shield that deflects the solar wind and protects the atmosphere from being slowly stripped away. The pressure within the Earth builds gently with depth, a silent, immense weight. At the base of the continental crust, about 30 kilometers down, the pressure is nearly 10,000 times that of the surface atmosphere. In the mantle, it reaches hundreds of thousands of atmospheres, and at the core mantle boundary, the pressure is over 1 million times greater. This is a force that does not crush, but patiently transforms, reshaping minerals into new, dense, crystalline forms. The gentle, rhythmic pulse of a geyser is a release of the Earth's pent-up thermal energy. Surface water seeps deep underground, where it is heated by hot rock. It becomes superheated but cannot boil immediately due to the pressure of the water column above it. Eventually, a small bubble of steam triggers a chain reaction, and the water flashes into vapor, pushing a column of water and steam up through the vent in a majestic, periodic fountain, a slow, heated breath. There are places where the Earth's inner heat whispers directly to the surface. In volcanic regions like Iceland or Yellowstone, geothermal gradients are much steeper. Here, water circulating through fractured rock is heated and can be tapped for gentle energy or rises naturally as hot springs and steaming fumaroles. These are thin places in the crust, where the boundary between the cool, solid surface and the warm, dynamic interior feels softly blurred. The Earth's magnetic field is not a fixed, rigid structure but a fluid, wandering presence. The magnetic poles drift slowly over time, and the field itself has gently reversed its polarity many times throughout Earth's history, with north becoming south and south becoming north. These reversals are not sudden flips, but a slow, graceful weakening and re-establishing over thousands of years, a quiet, rhythmic dance of the planet's invisible forces. The immense pressures deep within the Earth can create minerals that are never seen on the surface. In the lower mantle, common minerals like olivine transform into denser, more compact structures, such as bridgemanite. These high-pressure phases are stable only in the crushing depths, and if brought to the surface, they would quietly and rapidly revert to their low-pressure forms. They are secret minerals existing only in the planet's hidden, pressurized interior. The quiet energy of the Earth is the gentle engine for nearly all geological activity. It drives the convective currents in the mantle that move the tectonic plates. It fuels the volcanoes that build new land and recycle gases into the atmosphere. It generates the magnetic field that shelters life. This deep, persistent warmth is the planet's vital force, a slow, steady pulse that has shaped its surface, protected its life, and guided its evolution for billions of years. The ancient Earth, the Earth's earliest eon, is named for a mythical underworld, the Hadean. For its first several hundred million years, the planet was a vast global ocean of magma, constantly churned by colossal impacts. The sky was likely a dull, glowing orange, illuminated not by a clear sun, but by the incandescent rock vapor and steam of the atmosphere. It was a world of fluid fire, a gentle, molten beginning from which all solid things would later form. We don't know exactly when the first solid crust formed, as no rocks from the Hadean have survived. The oldest minerals we have are tiny, resilient zircons from Western Australia, dated to about 4.4 billion years ago. These crystals could only have formed from cooling magma, suggesting that patches of solid crust had already begun to gently congeal on the surface of the magma ocean, like a thin, fragile skin on a cooling cup of tea. The young Earth is thought to have been gifted its water by a gentle cosmic rain. Icy comets and water-rich asteroids, remnants from the outer solar system, bombarded the planet for millions of years. Upon impact, their frozen water would have flashed into steam, eventually cooling and condensing to form the first hot global ocean. The water you drink today may hold molecules that arrived in those ancient celestial deliveries. The late heavy bombardment was a period of intensified asteroid impacts around 4 billion years ago. For 100 million years or more, the inner solar system was a shooting gallery, with the Moon and Earth bearing the quiet scars. The vast maria, or dark plains on the Moon, are the solidified lava flows from these colossal impacts. The Earth, being larger, would have endured an even more dramatic pummeling, its early crust constantly recycled back into the mantle. The first continents were not the vast land masses we know today, but small, isolated islands of lighter rock. These proto-continents, composed largely of granite, formed as the mantle began to differentiate, with buoyant minerals like feldspar slowly accumulating into rafts of crust. They were the first, quiet whispers of the continents to come, fragile and fleeting in a world still dominated by volcanism and impact. The Earth's early atmosphere was a gentle but toxic blanket. It held no free oxygen, but was instead a thick haze of carbon dioxide, nitrogen, water vapor, and methane, perhaps with a faint, unpleasant smell of sulfur. This air would have been unbreathable to us, but it was a crucial insulator, keeping the young planet warm despite a fainter sun, a gentle greenhouse that cradled the planet's infancy. The first life emerged not in a gentle garden, but in a world of extreme conditions. The earliest fossil evidence from stromatolites in Australia dates back 3.5 billion years. These layered structures were built by colonies of cyanobacteria, simple microbes that began the quiet, revolutionary process of photosynthesis. They learned to turn sunlight, water, and carbon dioxide into energy, slowly setting the stage for a transformation of the entire planet. The Great Oxidation Event was a quiet, planetary revolution caused by the persistence of life. Over hundreds of millions of years, cyanobacteria gently pumped oxygen into the atmosphere as a waste product. This was a poison to most other ancient microbes, but it eventually allowed for the evolution of oxygen-breathing life. The iron dissolved in the oceans rusted out, forming vast banded iron formations that are now the source of our iron ore, a gentle but permanent chemical signature of life's influence. We don't know the precise shape of the first supercontinent, but we know the cycle had begun. A supercontinent named Valbara may have existed as early as 3.6 billion years ago, followed by others like and Kenoland. These were not the familiar shapes of Pangaea, but ancient, alien assemblies of the few cratons that had stabilized, drifting slowly across a world with vast, shallow seas and a still hostile land. The deep past is a story written in fragments, a quiet puzzle with most of its pieces lost. The Hadean world is known only from computer models and the chemical hints in ancient zircons. The first continents are but ghostly outlines in the most ancient gnarled rocks of the Canadian Shield and Western Australia. To study the ancient Earth is to practice a gentle form of listening, to hear the faintest of echoes from a time before memory, a world of fire and ice slowly giving way to the planet we know. The future, stone. The map of the world is a temporary arrangement, a single snapshot in a slow drifting album. The Atlantic Ocean is still gently widening while the Pacific is slowly closing. Africa is slowly drifting north, its gradual motion destined to close the Mediterranean Sea. Australia is creeping northward toward Asia. These are the quiet, current trajectories that will gently reshape the world over the next 50 million years. A slow-motion dance we can predict, but will never see. In about 50 million years, the Mediterranean Sea may be no more than a memory. The northward drift of the African plate will likely have gently collided with southern Europe, slowly crumpling the seabed and pushing up a new, grand mountain range. This future range, sometimes called the Mediterranean Mountains, may one day rival the Himalayas, a new spine of stone built from the quiet, relentless closure of an ancient sea. We don't know the exact configuration of the next supercontinent, but we can gently trace the current paths. One prevailing theory, known as Amasia, suggests the Americas will continue their westward drift, eventually closing the Pacific Ocean and colliding with Asia. Antarctica may drift north to join them, and Australia will have long since nestled against Eastern Asia. The world's land masses would then coalesce around the North Pole, a new, frozen-centered supercontinent. Another vision of the distant future is the supercontinent of Pangaea Proxima. In this model, the Atlantic Ocean stops widening and begins to slowly close, subducting beneath the Americas. This would bring the Americas back into a gentle collision with Europe and Africa, effectively recreating the ancient supercontinent of Pangaea, but in a slightly rotated orientation. It would be a quiet, cosmic return, a reweaving of the continental tapestry after a 250 million year separation. The long-term fate of the Hawaiian island chain is a gentle sinking. As the Pacific plate slowly carries each island away from the volcanic hotspot that created it, its volcanic fires go quiet. Erosion then takes over, patiently wearing down the peaks. Over millions of years, the majestic islands we know will be reduced to shallow seamounts, and eventually to flat-topped guyos on the deep ocean floor, their stories written in submerged, silent stone. The relentless process of erosion will continue its quiet work, regardless of where the continents travel. The Appalachian Mountains, already ancient and softened, will be worn down to a gentle, rolling plain. The Himalayas, still rising today, will eventually see their growth outpaced by erosion, and they too will be slowly, patiently reduced to stumps, their sediment carried to form new future landscapes in distant, unborn seas. On a far grander timescale, the Earth's tectonic engine may begin to slow. As the planet's internal heat gradually dissipates over hundreds of millions of years, the mantle convection that drives plate tectonics will grow weaker. The drift of continents may gently cease, and the planet may become a quieter, more static world, like Mars or Venus. The great geological cycles of renewal would slow to a near halt, a gentle closing of a dynamic chapter. The climate of these future worlds will be shaped by the new continental arrangements. A single, massive supercontinent would have a vast, dry interior with extreme temperatures, much like the interior of Pangaea once was. Ocean currents, which gently moderate our climate, would be completely rerouted. The distribution of life would be profoundly altered, following new corridors and facing new vast deserts. A world remade by the slow dance of stone. The relentless spin of the Earth is gradually slowing, thanks to the gentle tug of the Moon's gravity. In the far future, days will be longer. In another 100 million years, a day may be closer to 25 hours long. This slowing is a quiet, persistent change, a gradual winding down that will continue until, in the most distant future, the Earth's rotation and the Moon's orbit synchronize, leaving one face of our planet forever looking out at its silent companion. The ultimate future of the Earth's geology is tied to the life cycle of the Sun. In about 5 billion years, as the Sun expands into a red giant, the rising solar energy will gently but irrevocably break the silicate bonds in surface rocks. The continents will not be destroyed by collision or subduction, but will slowly be vaporized, returned to a molten state not seen since the Hadean Eon. It is the final, quiet close of the rock cycle, a gentle return to the fiery beginning from which it all arose. A living geology. The very air we breathe is a gentle gift from the partnership of geology and life. For billions of years, volcanoes have quietly outgassed carbon dioxide and water vapor, building the early atmosphere. Then ancient cyanobacteria began the slow process of photosynthesis, releasing oxygen as a gentle waste product. This oxygen transformed the planet, rusting the oceans and eventually creating the breathable air that now supports complex life. The atmosphere is a tapestry woven from the loom of rock and the thread of biology. The white cliffs of Dover are a beautiful monument to life's ability to shape the stone world. These vast white faces are composed almost entirely of the microscopic calcium carbonate shells of countless coccolithophores, tiny marine algae that lived in a warm, ancient sea. When they died, their delicate skeletons drifted slowly down through the water, accumulating in gentle, thick layers on the seafloor over millions of years, eventually compressed into the soft chalk we see today. The cycle of carbon, the element of life, is a gentle, planetary-scale dance between the living, the dead, and the rock. Carbon dioxide from the atmosphere dissolves in rainwater, forming a weak acid that slowly weathers silicate rocks. Rivers carry the dissolved ions to the sea, where organisms use them to build their shells. When these organisms die, their carbon-rich remains can sink to the seafloor and be buried, eventually turning into limestone, storing the carbon in a solid, quiet library for millions of years. Life does not merely exist on the Earth's surface, it actively shapes the very soil that anchors it. The first lichens and mosses that colonized bare rock began a quiet revolution. They secreted weak acids that slowly broke down the mineral grains, and when they died, their organic matter mixed with the rock dust, creating the first thin soils. This living skin then allowed for larger plants, whose roots further fractured the bedrock and whose decay continued to build the fertile ground that now blankets so much of the land. The vast banded iron formations of the world are a quiet, stone record of a planetary transformation. These red and grey layered rocks, the source of most of our iron ore, formed over 2 billion years ago. They precipitated from an ocean that was rich in dissolved iron, which rusted out when the first photosynthetic organisms began releasing free oxygen. The iron gently settled to the seafloor, layer by seasonal layer, capturing the moment when life quietly learned to alter the chemistry of the entire planet. We don't know all the ways that the deep earth and surface life are connected, but the links are profound. The nutrients that fertilize the great ocean blooms, like phosphorus and iron, are largely delivered by the gentle, global dust of eroded rock carried by wind and river from the continents. Even the clay minerals formed by weathering rocks are essential for soil health and carbon sequestration. The fertility of the biosphere is deeply rooted in the slow, geological crumbling of the continents. The climate of the Earth has been gently moderated by the rock cycle over vast stretches of time. When volcanic activity releases large amounts of carbon dioxide, warming the planet, the increased rainfall and temperature accelerate the chemical weathering of silicate rocks. This weathering process slowly draws CO2 out of the atmosphere, forming carbonate minerals that are carried to the ocean. This is a slow, negative feedback loop, a planetary thermostat that has helped keep the Earth habitable for billions of years. Coral reefs are living architecture built upon a geological foundation. The corals themselves are animals that extract calcium and carbonate ions from the seawater to build their hard, external skeletons of aragonite. Over generations, these skeletons accumulate into vast, complex limestone structures that become the foundation for the most biodiverse ecosystems in the ocean. The reef is both a living community and a growing geological formation, a vibrant city whose very streets are made from the bodies of its inhabitants. The gentle, rhythmic growth rings of a tree have a counterpart in the stone world. Varves are the thin, paired layers of silt and clay that accumulate on the bottom of glacial lakes. Each pair represents 1 year, with a light, coarse layer deposited during the summer melt and a dark, fine layer settling out from under the winter ice. Counting these varves, like counting tree rings, allows geologists to construct a precise timeline of the past, a quiet calendar written in the mud by the patient hand of climate and sedimentation. You are a part of this living geology. The calcium in your bones was likely once part of a limestone seabed. The phosphorus in your DNA may have been weathered from an ancient igneous rock. The salt in your tears is a memory of the primal ocean. Your body is not just living on the planet. It is composed of its elements, cycled and recycled through the great interconnected systems of rock, water, and air. You are a temporary, conscious gathering of the Earth's own substance, a gentle expression of its most dynamic and intertwined processes. And now, the stars begin to dim behind your thoughts. The deep canyons and silent crystalline caves grow soft and quiet in your mind's eye. We have drifted together through nearly 150 quiet truths about our patient planet. From the familiar ground beneath your feet to the Earth's incandescent iron heart. From the birth of a crystal to the slow drift of a continent. You have wandered through the rock cycle's endless rhythm, felt the pulse of water in stone, and touched the deep time of ancient Earth. You are part of this living geology. Not just standing upon it, but woven from it. The calcium in your bones was forged in the heart of a long-vanished star and settled in a silent seabed. The iron in your blood once rusted from the planet's early oceans, now pulsing within you. The very air you breathe has been cycled through volcanoes and forests for eons. Your atoms are ancient travelers on a long, slow journey, and for this moment, they have gathered to form you. Tonight, as you rest, the Earth continues its quiet, patient work. Tectonic plates drift at the speed of a growing fingernail. Crystals form in perfect darkness. Groundwater seeps through grains of sand. Sediment settles on a distant ocean floor, building the stone of a future world. And you are floating within it all, a small, warm presence in the vast, dark stillness, held by the same gravity that holds the mountains and guides the seas. If your mind is still drifting among these thoughts, that's perfectly okay. Let them go now. There is no need to hold on. There is no more to understand, only to rest. If you are still awake, you can watch the next chapter whenever you are ready. But for now, I hope you sleep well. I hope you dream of quiet canyons and slow-flowing stone. Dream softly. Good night.